right, guys. Well, good morning. Let's go ahead and get started. We have a fair amount to talk about. Continuing our discussion of gas liquid systems for single and multi-components. So I will say single and multiple component gas liquid systems. Last time we talked about volatility, which was a species or material's tendency to enter the gas phase or vapor phase, probably more accurate. We measure volatility using vapor pressure. Which is very important. And we can calculate vapor pressure one of a few ways, which I mentioned was probably the most common, Antoine's equation. Right, some log P star equals A minus B over T plus C, where those values are empirical constants. In your book, I believe it's table B4 in appendix B. We can also use Cox charts if you're so inclined. We can utilize the Clapeyron equation, which states that dP star dt is equal to negative delta HB, or the latent heat of vaporization, over the absolute temperature minus the relative specific molar volumes between the gas and the liquid phase. And if we wanted to, because it's a little easier, we can also rely on the Clausius-Clapeyron equation, which states that ln of P star is equal to negative delta HB over RT plus B, where B was an empirical constant, right? And so from this, we can graph ln of P star as our dependent variable. Our independent variable would be 1 over T, and the slope would give us negative delta HV over R, and the y-intercept would be our empirical constant B. So if we have a way of measuring vapor pressure as a function of temperature, you can take some data, graph it, and extract out the empirical constant B, as well as estimate the latent heat of vaporization. Any questions, anything I can clarify, thoughts, comments on those discussions on volatility and calculating vapor pressure? No, you guys are good? All right. Well, then we can keep moving and consider our next major subject area, looking at gas liquid systems with one condensible component. And so consider a system where I have a container. In that container, I've put water at the bottom. And if I let that container sit over time, I have air at the top. And I should have some amount of water as well that enters that air phase or the vapor phase at equilibrium. So in the liquid phase, I have water, and in the vapor phase, I have air and water. And in this system, I can consider only the water to be condensable, because if I'm assuming that my temperature is reasonable, let's say it's 25 degrees Celsius, my pressure is about 1 atmosphere, the air is not going to condense. And so I can consider a system like this to be, as I've stated earlier, it's a gas liquid system with one condensable component. If I were to apply Gibbs phase rule, which stated my degrees of freedom was 2 plus the number of components minus the number of phases, I would have 2 plus 2, because I have air and water, minus 2, which equals 2. Which means I would need to specify 2 variables to fully identify the system. So if I specify, or I can say with temperature and pressure specified, we have a fully specified system. So if I say my pressure is 1 atmosphere, my temperature is 25 degrees, that takes care of those 2 degrees of freedom. Yes. So if you want, I can, this is the number of phases. And this is the number of components. Right. So 2 things I need to specify. I specify temperature and pressure. So my system at this point is specified. So if I wanted to calculate the molar composition of the vapor phase, I could, because I know my temperature and my pressure. This requires application of what's known as Raoult's law. And this is extremely key equation. Raoult's law says if a gas at temperature T and pressure P contains a saturated vapor, meaning for all intents and purposes, we're at equilibrium, with mole fraction Y sub I. And if this is the only species, in the vapor phase that can condense, then the partial pressure of the gas or the vapor in the gas phase, you don't have to write this down, the equation will make sense too, equals the pure component vapor pressure at the system temperature. T. So this is the kind of key finding. The partial pressure of the vapor in the gas phase equals the pure component vapor pressure at system temperature T. For the species that is the only thing that can condense with mole fraction y sub I. So if I were to write that in an equation form, I would express Raoult's law as P sub I equals y sub I times P, which is the total pressure, times the mole fraction of that species, y sub I. And that has to equal P sub I star of T, which means that the partial pressure equals the vapor pressure of the pure component in that system at equilibrium. That's what we consider a saturated vapor. It holds as much as it can. Which means for this gas liquid system, I can find the mole fraction of water in air simply by calculating the vapor pressure of water at 25 degrees C. So let's change it up a little bit. Let's say I'm going to make it a little warmer, gets a little more vapor pressure from the water. So looking at the same system, but now I'm changing the temperature to 65 degrees C in 1 atmosphere. What is the molar composition of air and water, I'll say, in the gas phase? As always, I always encourage you, draw your problem. I got some water. Up here I have air and water. My temperature is 65 degrees Celsius. My pressure is 1 atmosphere. My question asks, calculate the molar composition of air and water in the gas phase. All right, so for this problem, I need to calculate the vapor pressure of water when my temperature is 65 degrees Celsius. So, since I like Antoine's equation, I'm going to use Antoine's equation. For water, I'm looking at the equation log P star equals A minus B over T plus C. My pressure is in millimeters of mercury. My temperature, and I like to kind of bracket the equals when I'm looking at only units, is in degrees Celsius. A is 7.96681. B is 1668.21. And C is 228. So plugging in, I have log of P star equals 7.96681 minus 1668.21 over T, which for this system needs to be in degrees Celsius, so 65 plus C, 228. So running through that really quick. Say 0.21 divided by 20 plus 228. 1 minus that. So I get from this log of P star equals 1.2401. Oh, I did the math wrong. One six six 8.21 divided by 65 plus 228. 7.96681 minus. This should be 2.2736. And my calculation was off. There it is. That makes more sense. So my P star is 187.61 millimeters of mercury, which converting that to atmospheres is 0.2468. All right, 2.69 atmospheres. It's about a quarter of an atmosphere is the vapor pressure of water at that temperature. So from Raoult's law, I know that y sub I times P equals P sub I star at my T, which in this case equals 0.2469. Now my pressure, I said, was what, 1 atmosphere? And therefore, my y sub I equals P sub I star over P, or 0.2469 atmospheres over 1 atmosphere, which is 0.2469. And this is my mole fraction of water. Now I know my mole fraction of air, since the only other component is 1 minus, or 1 minus 0.2469, which should be 0.7531. So those are my mole fractions. Was anyone able to follow that one? All right. One important thing to note is that when the vapor present in the gas is less than the saturation amount, we consider that system, or that vapor, superheated. And so for a superheated vapor, there is less vapor than what would exist in a saturated state. And so what can typically be done to make it saturated is you can cool that vapor, which is why in a lot of times we consider it superheated. So when it's cooled, such that, I hate that it does that, the vapor pressure, the amount of vapor reaches saturation, if I could spell in a way that you can read, Any subsequent cooling results in liquid formation, i.e. condensation. The temperature at which this occurs is referred to as the dew point. So I think the best way I can further illustrate and describe what's happening here is through some wonderful drawings. So let me go back to my same system, but in this case, I have air and water and no liquid. So let's say the T is sufficiently high. Let's say T is 120 degrees. Looking at this system, I can state that the mole fraction of water and air times the total pressure is less than what I would consider at saturation, which can be measured by the vapor pressure. Meaning there's more quote unquote room in that gas phase for water to exist. That's the way I kind of think of it in my head. But if I cool that system, T is decreased. Eventually, because the temperature is falling, the vapor pressure I would expect that system can have would also fall. However, I'm not taking out any water out of my system. It's a closed system. And so my mole fraction of water in my air isn't changing. Eventually, I'll get to the point where I'll reach saturation. And now, the mole fraction, or the amount of water that exists in the air, will equal that of saturation as I've cooled it, right? Because that saturation pressure will fall as a function of temperature, but the system's closed. The amount of water that exists in the system isn't. So eventually I'm going to get to the point where those systems equal. The only way I can continue to drop that temperature in that system is for liquid water to form. So any further cooling here, I'll zoom out. I don't like zooming out because it creates issues, but eventually what I'll start to see is this. The water will start to condense. And when this happens, I consider that temperature the dew point. So for water, we would find it forming at its dew point, or the temperature at which it will naturally condense. Does that make sense? You start to see that, right? Cools eventually. What exists in the vapor phase matches that of what can exist at saturation. The air becomes saturated because it gets cool. It can't hold as much water vapor. So any continual cooling will cause liquid water to form. Like I have two examples to choose. So let's look at this system. A stream of air at 100 degrees C and 5,200 millimeters mercury contains 10 volume percent water. Calculate the dew point in degrees Celsius. Calculate the percentage of vapor that condenses if the air is cooled to 80 degrees C at a constant pressure. What would be the final air composition? Let's look at this example together, and then we'll do one more in groups. So in this system, just to kind of for visual say, I have what, 10 volume percent water. So Y sub I of air is 0.9, Y of water is 0.1, and exists in a system. The temperature is 100 degrees C, and the pressure is 5,200 millimeters of mercury, which if I want to make that atmospheres to make it a little easier, 6.84 atmospheres. And I'm going to visualize this as going through a cooler. You really technically don't have to, but I'm going to. So I'm going to say the pressure doesn't change, but the temperature will, right? We're cooling it a little bit. And we're saying at some point we're going to have some liquid form. So off of that cooler, I could expect some amount of liquid water. And I want to know what is the mole fraction of air and water now leaving that system. Listen. Well, how do I find the dew point? That's the first question it asks. Calculate the dew point in degrees Celsius. Well, I stated earlier that when we're looking at the dew point, Y sub I P equals P sub I star, when the temperature is the dew point. So I know Y sub I, I know P, so I can, from what's given in the problem statement, so I can say, well, if I have 10 volume percent water, when my pressure is 5,200 millimeters of mercury or 6.84 atmospheres, therefore my vapor pressure at the dew point should equal 0.1 times 5,200 millimeters of mercury, or 520 millimeters of mercury. All right, so I got vapor pressure. How do I find the temperature? Well, I can work backwards using the Antoine's equation. Right? For my problem earlier, I said log P star is equal to A minus B over T plus C. Now I have P star and I'm looking for T. So I would say my log of 520 millimeters of mercury equals my constants 7.96681 minus 1668.21 over my temperature, which is what I'm looking for. Luckily, it's in degrees C, plus 228.
That's why it's the same, because we're still talking about air. Or are those always the constants?
For which ones? Antoine's?
A and B and C.
They're the same because we're still looking at water. If we were looking at a different species, we would have a different constants for the Antoine's equation. So I just have to solve this for t. So log of 520. And I like doing things in steps, even though it wastes paper. It keeps me from screwing up a lot of times. I have 2.716 equals 7.96681 minus 1668.21 over t plus 28, 228. So if I add the BC term and then I subtract what's over on the other side, I can say 1668.21 over t plus 228 equals 7.96681 minus 2.716. Which is 5.2508. Now, if I distribute, cross multiply, however you want to consider it, I can say 1668.21 equals 5.2508 t plus 228, which equals 5.2508 t plus 1197.184. If I solve that for t, I get t is equal to 89.7 degrees C. So I should have liquid formation. My temperature hits 89.7 degrees C. Everyone following so far? All right, so then the next part of the question. The percentage of vapor that condenses if the air is cooled to 80 degrees C at a constant pressure. What would be the final air composition? I think to solve this, it's actually easier probably to find that final air composition. So let's look at our system again. I know my dew point is at 89.7, and I know it leaves at 80 degrees C, right? So I go from some superheated vapor, let's say, and then it hits the dew point and liquid starts crashing out. As liquid essentially condenses, I have a system with liquid and water. And since they're both kind of existing in the same space, as liquid condenses, that whole time I have a saturated vapor in my system. And since I have a saturated vapor, in order to find the mole fraction of Y of water, I can rely once more on Raoult's law, which says right, Y sub I times P equals P sub I star at a given T. But now my T is 80 degrees C. So by solving my Antoine's equation again, I can find how much water vapor that system can hold. And that essentially tells me how much water vapor exists in there. So now going back to my Antoine's equation, I have log of P star equals 7.96681. I told you it would show up a lot. 8.21 over now 80 degrees C plus 228. So if I solve for my vapor pressure, I should get 355.3 millimeters of mercury for my vapor pressure of water at 80 degrees C. So to find my mole fraction of water and air, simply 355.3 millimeters of mercury over the total system pressure, which hasn't changed. It's still, what is it? 5,200 millimeters of mercury. Which is 0.068 or 6.8 mole percent, which, remember, is the same as volume percent. So I went from 10 volume percent down to 6.8. So then the question asks, the percentage of vapor that condensed. Well, if I started with 10 volume percent and I went to 6.8 volume percent, how much condensed? What? I can't hear you, I'm sorry. 32 volume percent? No, you're close. Move the decimal. 3.2 volume percent. So the amount that condensed right. So finishing up my figure, because I like to do that. I say this is now 0.068. And if now it's only 6.8, that means this should have shot up to 94.2 or 0.942. Stop doing that. Actually, just the better way to say that. I see why you said 32 now. Since 3.2 out of 10%, you're right, that is 32%. So 32% of what you started with did by going from 10% down to 6.8. But there was no amounts, right? You could have taken a basis and got to the same kind of amounts, or you didn't have to, depending on how you solve. How does that kind of make sense to you guys? All right. So what's a good application or example of how and when this occurs? What do you guys think? What? What's a good real world example of when this would what? Yeah, HVAC, air conditioning, right? That's why we have condensation all the time, right? You look at your car, you look at your house, right? You got the drain pipe because you got really humid air, especially here, and you cool it down, and 9 times out of 10, it's so close to 100% saturation. We'll talk about ways we can how that relates to relative humidity here in a second. But dropping that temp causes a whole lot of water to crush. That's definitely probably the most really straightforward example. All right, let's look at another example. I should say 3. All right, so in this example, I have liquid acetone in a sealed flask at 23 degrees Celsius with the gas above the acetone containing air and acetone vapor. The total pressure, 960 millimeters mercury. And we can assume that the mixture is at equilibrium. What is the partial pressure of acetone in the flask? If the vapor pressure is measured at 200 millimeters of mercury, what's the partial pressure of nitrogen? And how can you determine the boiling point of acetone in the flask? So where would you work on this one in your groups? On boards.
I guess we don't need that. Yeah. pressure that's due from. That's what I'm thinking. So this would give us the proportional reaction. So that's.
Basically, I shortcut it out.
Yeah. The next question asks for it. Yeah. So we take that. Originally, we used to buy stone. That one minus that is and then it's 0.21. Yeah. What is one minus that? One minus that. We don't need to do that yet because this is, I think it's 0.79. Don't we need to multiply that by? Well, but this is AR, we're trying to get. So we need to multiply. And then multiply it by. Wait, 0.7997 times 0.775. For the first.
All right, I'll give you guys a hand. We go Raoult's law. You just sit there and you're like calculating and calculating and calculating. You're like,
Yeah.
and like, and then when you realize it's like that's the code, you're like,
Yeah.
all right, so for the first part of this problem, I asked, what's the partial pressure? According to Raoult's law, when we're at saturation, the partial pressure P sub I is the phase pressure, P ice. So the vapor pressure in the problem is 200 millimeters. The partial pressure is 200 millimeters. That's it. No magic, no secret. Simply that. It's just they're just equivalent. We're at saturation, they're equivalent.
Yeah.
I know.
No, yeah.
Because that's the tendency. The tendency is to say, okay, let me get my equations together. We've got my calculator going.
Yeah.
Yeah, but I think we still need to do this to get there.
So we're saying we multiply the mass times one, multiply the mass times.
Yeah, 'cause-
So we're gonna move on.
I'm still
So over here, we want
right, functionally.
Right? Which is also why. You're close. You guys have any questions?
No.
All right.
Yeah.
All right, let me go back to the problem. Though, hold on, because I found some errors. Just gonna keep me up at night.
Yeah.
So looking at this example, I asked, we have our system of acetone. Oh, I don't want green. And air. A little bit of liquid acetone down here. The pressure of the system is 960 millimeters of mercury. And I stated that the vapor pressure of acetone is 200 millimeters of mercury. The first question I asked is, what's the partial pressure of acetone? Well, according to Raoult's law, P sub I equals Y sub I times P, which equals P sub I star at a given temperature, meaning P sub I equals P sub I star. So, answer the first question is simply the 200 millimeters of mercury, which was the vapor pressure of acetone given. So at saturation, the partial pressure is equal to the vapor pressure, all right? I'm gonna put that in a box. At saturation, the partial pressure of a species equals the vapor pressure of that species. Give me one of these. All right. The second part asked, what was the partial pressure of nitrogen in the system? Well, knowing the vapor pressure of acetone, I could find the mole fraction of acetone as the vapor pressure, partial pressure over the total pressure, or 200 millimeters of mercury over 960 millimeters of mercury. You should get about what? 0.20, 20%, meaning the mole fraction of air is 1 minus that, which was 0.8 or 80% air. Since I know that air is 79% nitrogen and 21% oxygen, the mole fraction of nitrogen is simply 79% of 80%, which should be like 60 something. .632. And therefore, going back to my equation, Raoult's law, P sub I is equal to Y sub I times P, or 0.632 times 960 millimeters of mercury. And so my partial pressure of nitrogen is 606.7 millimeters of mercury. All right. The last part of the question. How could you determine the boiling point of acetone in the flask under the as stated conditions? Let's look at this. In my system, I have liquid acetone, air, and acetone. And I say that Raoult's law applies such that Y sub I times P equals P sub I star at a given T. What happens if I increase my temperature? More specifically, what happens to the vapor pressure of my system as I increase my temperature? Does it go up, down, stay the same, go sideways? It goes up, right? So if I increase my system temperature, the vapor pressure of acetone will increase, meaning more acetone will go into the vapor, right? Is there a limit? Short answer, yes. That limit is the boiling point. Boiling point is 1 pi star. My vapor pressure equals the system pressure. So if I was to solve for the boiling point, I would plug the system pressure 960 and ambient pressure. Right? And that's why the boiling point of water, 1 atmosphere, is 100 degrees Celsius. Because at 100 degrees Celsius, the vapor pressure of water, meaning the air can handle all 6 So at that temperature, all the liquid goes to the vapor phase, and then you just have a single phase. Right? Because think about it the other way. If I had a superheated vapor and I started cooling it, eventually I would get to the dew point where condensation happens. Condensation happens, same point, when I reach saturation, which is when those match. It's a weird concept. It's not intuitive at all. When you see it, you think about it, you're like, okay, yeah, that kind of makes sense. Still not happy about it. But that's essentially the nature of a boiling point. It's when the vapor pressure meets the system pressure. Right? Think about it as, the vapor pressure is the pressure or force that the molecules are forcing on the vapor phase, or the gas phase, right? When that molecule can match the total system, it wins. And it all goes into the vapor phase. Right? I always think of it like tug of war. Yes, a hot plate also would have worked. Yeah, or the chart, the Google, that could have helped as well. There's a couple of things that we can also describe when it comes to vapor pressure. One being relative saturation, also known as relative humidity. S sub R is what's known as relative saturation, and it's a measure of the partial pressure of a species relative to the vapor pressure that it exhibits at a given temperature, right? So when we're looking at Raoult's law, the relative saturation is really 100%. And for all other values of saturation, we're looking at a relation. Right. So if I say, what's the relative humidity of water and air today? It's essentially a measure of the amount of water vapor that exists in the air compared to what it would exist at saturation. Right. It's why it's visible so much. Because 9 times 10% at this point in time in the year, we're usually sitting somewhere between like 70 and 95. Walk outside and it all starts condensing on you and all that. It's ugly. We can also consider things in terms of a molar saturation. Molar humidity. Which is the partial pressure of a species relative to the total pressure, which is essentially the moles of a vapor relative to the moles of vapor-free gas. Though admittedly, we don't use it a lot. We can also look at things in terms of absolute saturation or absolute humidity. S sub A, which is the partial pressure of a substance times the molecular weight of it over the amount that exists, not vapor, essentially the moles of vapor-free gas times its molecular weight, which is really just the mass of vapor over the mass of dry gas. A lot of these things are based on water. And the last one is looking at percent saturation. Which is S sub M over S sub M star, which is essentially looking at molar saturation compared to molar saturation when everything's fully saturated. And it's equal P sub I over P minus P sub I divided by P sub I star over P minus P sub I star. And if it's percent, we can multiply it times 100, make it a percentage. Let's look at an example. I have a gas tank, 10 mole percent styrene and 90 mole percent non-condensable gas. Whatever you want to call it. We made in the tank at 100 degrees Celsius and 1,000 millimeters of mercury. What would be the dew point, relative saturation, percent saturation of styrene? If the vapor pressure is 200 millimeters of mercury at that temperature. I want you guys to do this in groups again. And then when we're done with this, we'll talk about the exam.